surface of the sun is a photosphere. The light that we see radiates from here. Just above that is the chromosphere, where the density of matter is very low, you hear? On the next layer is the transition zone, where the sun's temperature is greatly blown out of proportion, and on the outermost layer you've got yourself the core, and the thinnest one, player. Just went over the sun's exterior, and now the next part is not inferior. Talking about the stuff that makes up the structure, the sun's interior. Convection zone is the outermost section, full of superheated gas and constant convection. Next layer down is the radiation zone, where towards the surface energy flows. Nuclear reactions occur in the core. It's the hottest area, 50 million K or more. That's how the layers. Now this rap is over. Now you know more about all things solar.
Solar magnetism and sunspots. Solar magnetism. The sun has a different type of rotation compared to the Earth. The difference is the magnetic field on the sun does not run north and south. Instead, the magnetism on the sun runs almost in a spiral fashion. This picture depicts the orientation of the magnetic flow on the sun. The Zeeman effect. The magnetic field on the sun can be precise in areas, because the energy in the molecules and ions on the sun can be split into more than one level. Spectral transmission lines can be split in this process. The amount of splitting due to the atom splitting is proportional to the strength of the magnetic field at that point. The increase of the spectral transmission lines is known as Zeeman splitting. We can measure the strength of the field by measuring the amount of Zeeman lines. Sunspots. The light from sunspots can be a sign of Zeeman splitting, as mentioned earlier. Sunspots are commonly associated with strong magnetic fields for this reason. The kinks that form from the Zeeman effects are typically what make sunspots. This is an example of a sunspot. This illustration depicts how exactly a sunspot would form, showing Zeeman splitting, as you can see through the 6 different pictures shown. When sunspots come in pairs, it typically means that they each have an opposite polarity. This means, for example, that one sunspot would be considered north, and the other sunspot would be considered south. This illustration is an example of how the sunspots, how one of them would be considered north, and how the opposite one would be considered south. Solar magnetism and sunspot go hand in hand because the magnetism on the sun makes sunspots. The sunspots are visible and measurable with technology, allowing us to figure out different magnetic fields around the sun.
Credit to Minute Physics for the idea. Here's Chris Serra talking with solar winds. Solar winds are charged streams of charged particles released from the sun. Now they mostly consist of protons and electrons. And they have a high energy, and the energy is measured in keV, or kilo electron volts. Now they range between 1.5 to 10 kilovolts. Now wait, what is a kilovolt? Well, a kilovolt breaks down into kilo for the metric system, and then EV is electron volt. Now the true meaning for electron volt is the energy equal to approximately 1.6 times 10 to the negative 19th joule. By definition, it is the amount of energy gained or lost by the charge of a single electron moved across an electric potential difference of 1 volt. Now, back to what we were saying. Now, solar winds escape due to high temperature, exactly 1 million Kelvin to be exact. Now it escapes the gravity, purple being the gravity here, and pink being the solar wind, because it has a higher energy than the gravity being pulling it in. Now, the effects of solar winds are, one effect is a heliosphere. The solar winds create heliospheres, an enormous bubble in the interstellar medium that surrounds the solar system. The heliosphere is a region of space dominated by the sun, a sort of bubble of charged particles in the space surrounding the solar system, blowing into the interstellar medium by the solar wind. So here we have the pink circle symbolizing the bubble, and the black specks symbolizing the solar system. And another effect that solar winds can have is geomagnetic storms, which is a temporary disturbance of the Earth's magnetic sphere caused by solar wind shock. What exactly is a storm? Well, it's the increase in the solar wind pressure initially compressed the magnetic sphere, and the solar wind magnetic fields interact with the Earth's magnetic field and transfers an increased energy into the magnetic sphere. Now, what storms have an effect on us is it knocks out huge power grids. So it could potentially knock out all the power to New York, or leaves us in the dark, which is sad. Thank you very much. This has been Chris Sura with Solar Winds. You can refer back to my notes in the PowerPoint. Solar Winds. Thank you, and credit to Minute Physics. Mine isn't as good, but it's getting there.